this video, we're going to demo doing inference on paired data. The data come from the high school and beyond survey. These are 200 observations that were randomly sampled from this survey. Let's start by uploading the data. We want to locate the data set on our computer. It's a CSV file. And then we want to import that into our studio. And once it's been imported into our studio, you should be able to find that data file in your Files pane. The next step is going to be importing the data set into your Workspace so that it can be usable for the analysis. So I want to click from Text File, find the data set that I want to import, click Open. You want to make sure that if your data set has a header, which it most likely will, that the radio button next to Yes is selected, and you can see under the lower window here that the first row is bolded, indicating that this is not data, but actually names of the variables in your data set. Lastly, we click Import, and we can see our data set here. We have 200 observations in our data set. Each row, in other words, each case, represents a student who took this survey. We have their reading test score, writing test score, math and science test scores, and their social studies test scores, along with some variables on their socioeconomic status, the type of school and the type of program they're in, and some other demographic variables like their race and gender. The research question we want to answer is there a difference between the average reading and writing test score? We can see for each student that we have these data for their reading and writing test scores, but something that we need to keep in mind is that for a given student, their reading and writing test score are not going to be independent because it's the same student that's taking both of the exams. So in order to be able to complete this analysis, the first thing we need to do is to create a new variable that has the difference between the reading and writing test scores for each student. Then our null hypothesis would be that this average difference is equal to 0, indicating that the average difference between the reading and writing test scores is 0, and the alternative, since we're only looking for a difference, is going to be two-sided. So let's start by creating this variable. In my new data set, I want to create a new variable. Let's call that difference reading writing. So diff underscore RW. Remember, in your variable names, you don't want to use spaces. And we'll say that this is equal to the reading score, labeled read, minus, from the same data set, the writing score. And if we click on the data over here, you can see that we used to have 11 variables, now we have 12, and we can scroll over and see the new variable that we created. For a given student, for example, let's look at the first one. Their reading score is 57 minus writing score is 52, giving a difference of 5. For the second one, that's 68 minus 59, giving a difference of 9, so on and so forth for each one of the students. Now we can load our inference function. And once that's loaded, you'll be able to see that in your Workspace as well. And finally, we're actually ready to complete this hypothesis test. So I start by writing the name of my function, and then in parentheses, I'm going to enter in my arguments. The data that I'm using comes from the data set HSB2, and the variable of interest is a new variable that I created. I want to do inference on the mean, since we're interested in the average score. My null value is 0. Since I'm looking for a difference, I'm looking for any difference between these two test scores. I want to do a hypothesis test. My alternative hypothesis is two-sided, since we're looking for a difference. And lastly, let's start by using a theoretical method. The function runs, and we can see over here that the differences are nearly normally distributed, so we really don't need to worry about extreme skew here. We have a large sample size anyway. We have 200 observations. The observed difference between these two, the observed average difference between these two test scores is negative 0.545. The standard deviation is about 8.9, and I have data from 200 students. My null hypothesis says that the average difference is 0. The alternative hypothesis says that the average difference is different than 0. The function calculates my standard error and also calculates a z-score for me. This is a z-statistic for the test since we have a large sample. as the observed mean minus the null value divided by the standard error. With a smallish z-score, we have a pretty large p-value. With such a large p-value, we would fail to reject the null hypothesis and conclude that these data do not provide convincing evidence of a difference between the average reading and writing test scores. We can also evaluate this using a confidence interval. So in a confidence interval, the null value and an alternative hypothesis are irrelevant, so we can get rid of these. And all I need to do is to change my type from hypothesis test to a confidence interval, and I can see that the confidence interval suggests we're 95% confident that the average difference between reading and writing test scores is between -1.8 and +0.7. In this case, the interval contains 0, hence we wouldn't want to reject the null hypothesis of the average difference being 0. The confidence interval and the hypothesis test agree with each other. We can also use a simulation method here, and when we're doing a confidence interval, simulation basically means doing a bootstrap sample. So we start with these differences that we calculated. We want to take bootstrap samples from this data to samples of 200 observations sampled with replacement from the original data. And for each one of these bootstrap samples, we calculate a bootstrap mean, and we repeat this many, many times. The inference function does so about 10,000 times and constructs a bootstrap distribution for us. The bootstrap interval of roughly -1.8 to +0.7 is very similar to the earlier theoretical interval as well. Lastly, to complete the story, we can do a simulation-based hypothesis test as well. For that, we want to make sure that we add our null value and our alternative as arguments to the inference function. And all that this randomization test is doing is taking that bootstrap distribution from earlier and shifting it such that the center of the distribution, we can see over here in the plots pane, to centering it at the null value of 0. According to this, the observed difference of -0.545 is really not that unusual a value. It's pretty close to the center, and hence our p-value comes out to be large, meaning that we would fail to reject the null hypothesis. We can see that all of these approaches agree with each other. Once I'm done with my analysis, I want to make sure that I incorporate all of this in my report. So what I want to do here is in my data section, I want to make sure that I read the data in, and that I also, at some point in my document, want to make sure that I read the inference function in as well. I want to make sure that I create this new variable over here with some text about why I would want to do so. And in the inference section of your report, you want to include your results from the theoretical and the simulation inference functions. And finally, the report looks as such, with a little bit of beefing up of the report with some introduction and exploratory data analysis and a conclusion. I'm pretty much done with my project. I hope that this video has been helpful for doing inference on paired data using R. Thanks for watching.